So the two p's, and of course if you remember we have three orbitals in the 2p subshell. We have the pz, which my z is horizontal. Okay, so here's the positive unshaded, the negative shaded. We got the px, which is going vertically, so positive unshaded, negative shaded, and then the py, which goes in and out, which I'll draw this way, the negative shaded coming at us, the positive unshaded going away from us. Now, we already talked in the previous movie about the bonding orbitals from these. So thus we can have the pz on one atom with the pz from the other atom. And notice now I'm drawing these as in phase, the positive and the positive coming together. So that gives us the sigma 2p that we've seen before. Now, how do we draw the antibonding? Well, the antibonding is where they're out of phase. So there we've got the positive here, but the negative here. Positive and negative cancel each other out. And so the sigma star 2p here would look like this. Nothing in between. You'll most of the time you'll see this drawn with teeny little nubbins in between. I'm not going to mess around with that. Nice and simple in between. They wipe each other out because you have the positive and the negative. You do have the negative lobe of the left-hand atom there in the antibonding space, the positive lobe of the right-hand atom there, also defining the antibonding space. So there's the pz on one, pz on the other. In phase, what we saw before, a sigma 2p bonding orbital. Now the out of phase to give us the antibonding. Now let's start looking at the px's. Now if you remember, when the px's come together, they're not pointing at each other. They are up and down. They're parallel to each other. So we don't get sigma, we get pi. So we can do the in phase combination that again you've seen before. There's the negative bonding lobe, the positive bonding lobe, giving us that pi 2p bonding. And now, of course, with the px's, you can have the outer phase. So there's positive on top, negative on the bottom, and then negative on the top, positive on the bottom. You're not going to get any overlap there with the outer phase. So what we see is nothing in between. But we do have what was left of the little positive lobe here, there, what was left of the negative lobe there, what was left of the negative lobe on the first one there, what was left of the positive lobe there. Okay, so again, simplistically, you can see how we've got the in phase, the nice bonding combination there, and the out of phase, nothing in between. Here, in phase, bonding, the electrons can see both nuclei. Here electrons would not see both nuclei, they're just seeing the one. So you can still apply our simplistic approach to it. Much nicer to think of it as in an out of phase. Now for the py was just rotation by 90 degrees of px. So we can have the in phase combination giving us what I like to think of, if you think of this as being a hot dog bun without a sausage, there's the hot dog bun without the sausage, rotated by 90 degrees. You've still got a big gap here that would be the line that connects the nuclei. So this is a pi 2p, just like this one, because this rotated by 90, you get that one. And then the outer phase, same idea. You would just have the sigma 2p antibonding obtained by rotating these by 90 degrees. Hopefully you can see the relationship between the px and the py. Kind of tough to see, but a lot of times, but not that important that you see it, except of course when talking about triple bonds. What's important for now is that you can see the following. When we have a p subshell, we have a sigma and 2 pi bonding orbitals, and the corresponding sigma star and 2 pi star anti-bonding orbitals. Now when we put all those together, we get a little energy diagram that looks like this. The 2p electrons, whether it's px, py, or pz, are of course degenerate, those p orbitals, but then when they overlap, we lose the degeneracy. We have the sigma and the sigma star, which generally, without any messing around, are the low energy for the bonding and the high energy for the anti-bonding, because The sigma, the one right between the atoms, is of course much nicer overlap than the pi. But you see the two pi degenerate bonding, one of those from the pi px's, one from the py's, and the degenerate antibonding. Degenerate, remember, means same energy. So if I was to look at, for example, O2, O2 we think of as being the helium nucleus, don't care, 2s2, 2p4. So here's our 2s and our 2s, our 2p and our 2p's. The 2s is overlapping, as we saw in the previous movie, sigma 2s, sigma 2s star. 2p's overlapping, as we've seen here, sigma 2p, 2 pi, 2p. So 3 bonding orbitals and 3 analogous antibonding orbitals. Throw in the electrons for each oxygen atom. Now let's think of O2. We got 2, 4, 6, 7, 8, 9, 10, 11, 12 electrons to put in. So 2 and 2 each in the ones from the sigma 2s, 2 more in the sigma 2p. Now let's count these. 7th, 8th, 9th, 10th. Remember, they go in individually according to Hund's rule. Still got 2 more electrons. Both go into the pi 2p star, the antibonding pi 2p, because these are of equal energy, you get 1 in each. Electron configuration, sigma 2s2, sigma star 2s2, sigma 2p 2, pi 2p 1, 2, 3, 4, notice that, and then 2 in the pi star 2p. Bond order, we've got 8 bonding, 2, 4, plus 4 is 8. 4 anti-bonding, 2 plus 2 is 4, 8 minus 4 over 2 is 2, double bond, gee whiz, how wonderful, and so on. But what's significant about O2, and this was one of the driving forces that led people to realize you needed something a little bit more than just Lewis structures, was that if you take oxygen gas, well actually liquid oxygen, liquefied oxygen gas, it's a blue liquid, it's paramagnetic. It gets attracted to a magnetic field. Things are paramagnetic when they have unpaired electrons. Lewis structures don't tell you about unpaired electrons for things like O2, but using our MO theory, we can see there's 2 unpaired electrons in O2. Double bond, as we would think anyway. There's the electron configuration taken from this little series. 2 unpaired electrons, explaining the paramagnetism of O2. Easy, huh? Well, of course, you know it can't be totally easy. I debated whether or not to even bring this complicating factor in, but I thought, what the heck, it's an extension topic, so I might as well. And that is that when orbitals overlap, they overlap better the closer they are in energy. And this is something that, if we were talking about heteronuclear diatomics, would come in there significantly. The further apart orbitals are, the worse they overlap, even if they've got just the right symmetry and everything. Now, the converse of that is that, of course, the closer they are in energy, the better they overlap. Now, when you look at boron, carbon, and nitrogen, there isn't a huge difference in energy between the 2s and the 2p orbitals on each atom. And so what that means is that, as we talked about in the first movie, S interacts nicely with S, PZ with PZ, but PZ can interact with S as well. And so when the S and the p orbitals on an atom are close in energy, you get what's called mixing between the S and the PZ sigma orbitals. Now, this affects the energy levels quite a bit. The one we're most interested in is that the energy of the sigma 2p orbital is raised such that it goes above the pi 2p. So when you're dealing with boron, carbon, and nitrogen, because the 2p and the 2s are relatively close in energy, the sigma 2p goes up. There is actually also a concomitant decrease in these ones, but we don't worry too much about that because that doesn't change the orbital. It does change where the sigma 2p is. Now, oxygen and fluorine, the 2s and the 2p's, are much different in energy, so you don't get nearly this level of mixing. So anyway, let's look at, for example, C2, just to see how it changes things. Same principle overall. C2 helium, don't care, 2s2, 2p2. Let's throw those electrons into the picture. And now let's think about C2. Each carbon gives us 4 electrons, so we need 8 electrons in C2. So 2 in the sigma 2s, 2 in the sigma star 2s. And now we've got 4 electrons left that go individually, of course, into those pi 2p's. So C2, sigma 2s2, sigma star 2s2, pi 2p4. Bond order is 2, and even if we'd used the previous filling mechanism, we would still get the bond order of 2. But what's noticeable about this is that C2 is not paramagnetic. It's diamagnetic because there's no unpaired electrons in the molecule. If we'd put 2 electrons in the sigma 2p and then 1 each in the pi 2p's, it would have been paramagnetic. So C2, unexpectedly, until one realizes about this mixing, diamagnetic in the same way that O2's paramagnetism could be nicely explained.